Okay, so let's try another problem on trust. This time it's three unknowns and the displacements are on different joints. Okay, so we have this problem here, still an axial member problem. We have how many unknowns here? 1, 2, and then 3 because this is only roller support. So this support can only resist this loading along horizontal, while this joint can displace on both on x and y. The rest are restrained. Okay. So as with the previous problem, we we assigned a number to each joint and the corresponding degrees of freedom. So for example, here, let's assign joint 1 here, joint 2 here, joint 3, joint 4. And member 1 is this, member 2 is this, member 3, member 4, member 5. So technically you can assign a different set of or sequence of numbering for each but again you should be consistent. So with that, since now I already assigned the member number and joint number, therefore the degrees of freedom will follow. So for K1, this one, the stiffness is 1, 2, 3, 4, right? So 1, 2, 3, 4. Okay. Member 2, this one. So it's joint 1 and 3, having degrees of freedom 1, 2, 5, 6. Okay? 1, 2, 5, 6. Okay, so where is K2? This one. K2, 1, 2, 5, 6. 1, 2, 5, 6. Okay, next, member 3. Okay. So I'll be connecting joint 2 and joint 3 with the degrees of freedom 3, 4, 5, 6. Okay? 3, 4, 5, 6. So 3, 4, 5, 6. Okay, take note of the sequence, no? That means my start node is 2, my end node is 3. So the direction is something like this. For node 1, the direction is this. For member 2, the direction is this, going down. Okay. Next is member 4. This is member 4. So the joint is 2, 4. Therefore, 3, 4, 7, 8. So 3, 4, 7, 8. So the direction is going down. Okay. And last is for member 5. Member 5. So I'll be connecting 1 and 4, having degrees of freedom 1, 2, 7, 8. 1, 2, 7, 8. 1, 2, 7, 8. Okay? Now, what is our structure matrix, stiffness matrix? I told you the displacements will be 3. Therefore, the size of S is 3 by 3. So I will prepare a matrix size 3 by 3. And what is the corresponding degrees of freedom? According to our problem, the degrees of freedom are 1, 2, and 4. Because 3 is horizontal. So this structure can displace by vertical, which is 4. Okay, degrees of freedom 4. Okay? Okay, so 1, 2, 4. That means all the degrees of freedom having 1, 2, 4 in each stiffness matrix will be obtained. Okay, so 1, 2, 4. 1, 2. So member 1 has both 1, 2, 4. Okay, so we will get all these elements here. Okay. Member 2 has only 1 and 2. So get these element values here. Member 3 has only 4. So only one value will be get here. Will be obtained. Member 4 has only 4 also. So only one value for that. And member 5 has only 1, 2. Okay. Okay, so I like to look at it for a while. Okay, so our material properties are this. E is 70 gigapascal and area is 4,000 millimeters square. And our coordinates are this. So we have 8 meters, 6 meter, 4 meter. Take note this 2 is not connected here. They are not connected here. Okay. Okay, so I already prepared a STAAD model for this, just this one. Okay, so just input all the coordinates like here, and then this is the properties. So 70 gigapascal, therefore I created a material for 70 gigapascal. Okay, so when I open this, okay, take note of the Young's modulus. So this is the corresponding Young's modulus for 70 gigapascal. Okay. Don't mind this, no. The what's important is the Young's modulus right now. Next is the properties. So the given is 4,000 millimeters square. So if you convert 4,000 millimeters square, diba? 4,000 is equal to pi d square over 4. So transpose here, divide by pi, and square root of d, you get this. 71.36 millimeter. Okay. Don't be misled. It's concrete, but take note the material assigned here is the material I created for 70 gigapascal. Okay. For the supports, I created two supports because we have pin supports here and a roller here. So roller is fixed butt. Okay. Fixed butt because we only have restraint on x direction. So therefore the other degrees of freedom will be released. Okay? Other degrees of freedom will be released. And that's it for the supports. And for the loading, okay, these are the loading. 400 downwards and 800 to the right. Okay, so that's it. And then analyze. Then once done, this is the corresponding displacement. Okay, so we should be getting the same sets of displacement. Okay, so how do we implement that in our spreadsheet? Okay, so let's do this. For member 1, I copy paste the convention that we used. Member 1 is this. Since 1, 2, 3, 4 going to the left, therefore my x is -6. Okay. Okay. Then area is 4,000, E is 70. How about member 2? What is my coordinates? Going downward also. So that is 6, no? This is 6, yeah. So -6 and my y is -8. Okay. Area is 4,000. 70. Okay, member 3. How about member 3? -8. So 0 ang x. 0x -8 for the y. Okay, so it's since the spreadsheet cannot read, cannot divide 0, so I'll try 0.0001 just to have some value, no? To avoid numerical error. 4070. Member 4. Okay, so our degrees of freedom is 3, 4, 7, 8. So going downward again. So that will be positive 10, negative 8. Member 4 is positive 10, negative 8. Okay, 4,000. Okay, last is member 5. Member 5. Okay, I should change this as member 5. Member 5 is positive 4, negative 8. Positive 4, negative 8. 4,000. Okay, that's it. So we now have the stiffness matrix of each element. Okay, so how about the S? So how do we get the S? How do we get the S? So I'll prepare 3 by 3. So let's prepare a 3 by 3. 1, 2, 3. Okay. Okay, so let's assign a number for our S, 1, 2, 4. And for member 1, this should be, I'll return the color to its to green. So to avoid, oops, to avoid confusion. Okay, so member 1 is 1, 2, 3, 4. 1, 2, 3, 4. Member 2, 1, 2, 5, 6. This should be 1, 2, 5, 6. For member 3, 3, 4, 5, 6. Okay, 3, 4, 5, 6. 3, 4, 5, 6. For member 4, 3, 4, 7, 8. Okay, that's it. Okay. Then last is for member 5, 1, 2, 7, 8. 1, 2, 7, 8. Okay, so that will lead us in creating our S. So all 1 and 1. So let's gather all 1 and 1. So this is 1 and 1, okay? Plus 1 and 1 plus okay. No more. This one. Okay. Next is so I'll prioritize the diagonal first, okay? All 2 and 2. So all 2 and 2 because 2 and 2 for the diagonal. Okay, 2 and 2. So I can get this plus zoom in natin. Ayan. 2 and 2. This one. 2 and 2. This one. No more. Enter. Yeah. Last is, sorry, 4 and 4. All 4 and 4. 4 and 4. This one is 4 and 4. Okay. Plus 4 and 4. Plus, no more. This one. 4 and 4. Okay. Why do I prioritize diagonal? Remember, S is typically symmetric. Okay. So 2 and 2. Okay, let's proceed with 2 and 2. Sorry, 2 and 1. So 2 and 1. This one is 2 and 1 plus 2 and 1 is this. Okay. Enter. All 4 and 1. 4 and 1. Okay, 4 and 1. No more. This one, 4 and 1. Then all 4 and 2. 4 and 2. 4 and 2. Is there a 4 and 2? This one? Yeah, this one. This is 4 and 2. 4 and 2. Okay. How about 1 and 2? 1 and 2 equals 1 and 2. 1 and 2. This one. Right? Column 1, row 2. Plus 1 and 2. This one. Column 1, row 2. 1 and 4. Column 1, row 4. Column 1, row 4. Think this one. Right? Column 1, row 4. No more? Okay, no more. Then, last is 2, 4. Column 2, row 4. Column 2, row 4. No, nothing here. This one only. Column 2, row 4. This one, 0. Okay? So what do you notice? Am I right? The structure stiffness matrix is symmetrical. Right? So, this is, when we say symmetrical, so this is 0, this is also 0. This is 0, this is also 0. This is 13,440, this is also 13,440. Okay? So, after getting S, let's establish P. So, where does our P act? Okay, since our S is 1, 2, 4, therefore, our P should be consistently 1, 2, 4 also. Okay, P equals 1, 2, 4. Okay, so which force is acting along 1? Degrees of freedom 1. It's 800, right? Sorry. Yeah, 800. So this is 800. What force is acting along degrees of freedom 2? So that is 400. This one, negative 400. And finally, what force is acting on degrees of freedom 4? So negative 400 also. So 800, negative 400. So let's set up here. 800, negative 400. This is our P. Okay, so we have P, we had S, we can now get D. So we have 3 by 3 and 3 by 3, so our D is 3 by 1. Okay. First, we need to get the inverse of S. So this is S inverse. So I'll select this. Okay. And then equals meanverse. Open parenthesis. Select the S matrix. Close, and then Control Shift Enter. Okay. Then multiply with S. Okay. Sorry, with P. So equals M mult. Select the S inverse, comma, and then select the P vector. Close parenthesis. Then Control Shift Enter. Okay, so that's it. We have now our displacement. Okay, so we have this displacement now. But let's check our stiffness matrix, because I'm getting this 1549, while in STAAD I'm getting 1299. Okay, so there's must be something wrong. Okay, 21. Okay, our S should be 900. Okay, this one here, 900. So I think there's something missing. 21, 21, 21. So F2. Okay, 21. Let me check. 21. Okay. 21. Okay. Okay, I forgot this. This one, this item. So let's add that. Plus this one. This is also 21. Okay, and then enter. Okay, so if I correct that, this should also be corrected. So plus this one, 1, 2. Okay. Okay, so that's it. We were now able to get the same displacement with STAAD. So this should be 0.0128 meter going to the right, negative 0.009 meter going down, because this is 124, right? Okay. Degrees of freedom 2. Then negative 0.009 also going down. Okay. So 1299, which is consistent with our STAAD. 1299. Going down both. Okay. Let's try getting member force. Okay. So let's set up member force. Say, what do we want to get? I wanted to get, so I'll proceed with beam results to get the local or even global member force. So let's try here. So beam 3. So you should have 448 as axial force. Okay. So beam 3. But this is beam what? Beam 5, no? Beam 5. Okay, maybe I'll try to double click. Okay. Yeah, this one. Snapshot this. So I selected this, and this is highlighted, global forces. No, local forces. Okay, so I'll select. I should not select bending. Okay, shear Y. Anyway, so I'll just click on local force. Okay, let's try here. Anyway, as you notice, although we have bending moment diagram, it's very negligible, no? Almost zero. Okay. Okay, so I'll set up beam 5. Beam 5, right? That is member 5. So our equation to get the global force is F equals kV, right? kV. So I'll set up my V matrix. V for 5. So that should be 3, 4, 5. So which corresponds to 1, 2, 7, 8. So that will be 1, 2, 7, 8. And our displacement for 1 and 2 is this. Okay, I'll get that. Get this. For 2 is this. Okay, so this is 1, 2, 4. So 7, 8 is of course 0 because we have restraint there. Now what is our K? Local. This one is our K. I mean global. Sorry. Global stiffness matrix for our member. So we have our K, we have our V vector. So we can now get F. So F is just simply multiplying 1, 2, 3, 4. So equals M mult multiply this K, global stiffness K, to the global displacement. Okay, then Control Shift Enter. Okay, so we are getting the global force on member 5, while this one is local force already. So how do we resolve that? Find the resultant. Okay, how do we solve the resultant there? So maybe equals this square plus this square, and then find the square root. SQRT. Okay, I'm getting 448. So almost the same. Okay, 448.07. Okay, so 448.07. STAAD also gets 448.07. Okay, so that means after getting the global, this one is the global force FXFY. Okay, this 1, 2, 7, 8, right? So this is 200, and then this is negative 400. So in order to get the actual, so find the resultant of this, which is this. Okay, as you notice, we have same magnitude on the other end, so you can come up with the same actual force. Okay,